Well, good afternoon, 8th and ninth. I am putting this video on. I put one on earlier this morning, and now this is let's see, Wednesday afternoon, and no one has looked at it yet. So I'm wondering, maybe nobody will look at this video. I hope you do. But let me tell you something that's off the side from this video. Miss Bethany wants to have some yearbook articles. And I mentioned that in yesterday's video, but you don't know this because you haven't looked at yesterday's video yet. But I said there I'd like to have some volunteers. And now I've changed my tune. Since no one's volunteered, well then I want all of you to write a yearbook article to put in the yearbook, so that you just hand them in. And now this is different 8th grade than your little saying there at the end of the year to graduate. This is different than that. This is just a yearbook article about the year. And so I'll give you some suggestions. You can write about, let's say, a certain subject you like. Maybe you want to write about Mr. Lau and the music classes. Maybe you'd like to write a little article about, let's see, coronavirus, homeschool versus conventional school, or I guess you call this conventional school. Yeah, you use your imagination. And so all of you write a little article and send it to Bethany, and she will choose. I don't know if she'll be able to do all of them or not, but you know, she would choose between it. Now, if some of you have some kind of ailment or sickness, or if you've caught the coronavirus and you can't write this article, then you text me and let me know that you won't be sending Bethany, or you won't be bringing an article for Bethany. But we need yearbook articles, and you need to do this, okay? 8th and 9th grade, and I've already signed the 10th grade. They have to do it too. So everybody needs to write an article, and Miss Bethany can just pull from this pool of piles of articles. And I don't know, maybe some of them will get published in the, I don't know what, in the Mount Olive newsletter. Mount Olive School newsletter. I don't know, but that's aside the point. We're back to Science Today. And I want to mention something as I was thinking about the sun, like we studied yesterday, and I was thinking about how it is in comparison. I thought, you know what? We learned this back when we studied the planets. We drew it out here in the gym. You know, the sun wouldn't even fit on. That gives us a perspective. The sun should have been 46 foot in diameter. And we just had to put a little slice along the wall there. And the biggest, well, you know, the Earth was just what? A little dot in comparison. The biggest planet was only what? I mean, about 4 foot in diameter. So in comparison, 4 foot versus 46 feet, that gives us a little feel of how big a star is in comparison to the rest of our world. Okay, now today we're going to talk more about just stars. Okay, so if you look on page 404, or actually look on 405, they have rated stars by their color. Now, you probably need a telescope. That's probably the most valuable thing there is to study stars, is something that will be able to tell you the color. And I've noticed that, and the little that I've played with a telescope, or that other people have actually helped me with using a telescope, is you can see the colors much clearer through a telescope than what you can just looking with your naked eye outside at night. The coldest stars, no, our sun is not the hottest star, okay? So let me look at the temp on page 405, 16.1 gives you the temperatures, and you've got a letter. M is less than 5,500 degrees. 5,500 to 8,000 degrees is a K star, and 8,000 to 10,000 is a G star. They have each one listed there with a letter. And I want to tell you that the blue star is is the hottest. If you turn your page over to 407, I'm jumping just a little bit ahead, but you look over there and you will see the hottest is blue, then you've got green, yellow, all the way over. The coldest is red. Okay, so get that kind of in your head. The hottest is blue, coldest is red. Now that might not seem right to you, but that's the way it is. You think of something being hot being red, but if you think of let me see here, boys. When you think about a torch, and you girls maybe watch this too, when you light up a torch, you can make an orange or a red flame, but when you really make that torch hot, it gets blue. And that is when you can cut metal with it. So the bluer the torch, the hotter it is. And so that's the way it helps you identify with stars. The blue ones are the hot ones. Nowadays, astronomers, I'm back on page 405. Nowadays, astronomers look at individual wavelengths of light in the process called spectroscopy. Spectroscopy. Spectroscopy is the best that I can pronounce that word. It's pronounced out there for you. You see, that helps them decide what bracket to put the star in. They not only vary in color and heat, stars also vary in brightness. You can see that at the bottom of 405. It says you get a pretty interesting result now. Not only do stars vary by color, but also by brightness, and that's easy to see. When you go outside, you can see some stars are brighter than other stars, and that basically has to do, well, why is that? There we go, I asked you the question, why is that? And that has to do with two things. One is how much light the star is throwing out, and the second thing is how much or how far away it is. How much light it's emitting and how far away it is. You know, the moon doesn't give off any light. It only reflects off the sun. The earth doesn't emit any light. It doesn't throw out any light. The planets don't throw out any light. We can only view them from the light that the sun throws on them. Well, that's kind of the way the stars are. Some throw off a lot more light than others. Some emit tons of light, and others do. I guess tons is the way to describe light. But anyhow, and some are so far away that they can't be seen unless you have a telescope. Okay, that brings me down to the next point on 406 is absolute magnitude. This is a word that's underlined, so you have to know that. That is, absolute magnitude is the brightness of a star corrected by distance on the scale of -8 to +19. The smaller the number, the brighter the star. So that means that if you see a -5 and a +5, the -5 is brighter than the +5. Okay, the smaller the number, the brighter the star. The absolute magnitude. Now let's look at the apparent magnitude. That's what it looks like from our position on Earth. Okay. So the apparent magnitude is the brightness as seen in the night sky. The smaller the number, the brighter the star. Still works the same way. So while the sun has an absolute magnitude of +5, its apparent magnitude is -27. Okay, the sun isn't such a bright star. It's a +5. So it's rating up there. It's not a very bright star in comparison to other stars. But to us, its apparent magnitude, what we can see, we say, oh, the sun is the brightest star. Well, that's because it's just real close. You know, you take a flashlight and you put it out here on the other side of your yard, and it's not real bright. But you bring that flashlight right up here and shine it in my eyes, it's bright. Or if you take that flashlight and go a mile away on top of the hill and shine it back toward me, I might be able to see it without binoculars, but probably not. But you bring that flashlight here and hold it about 6 inches away from me, and it's bright. You get the point? That's the way stars are. Those ones that are way out there may be bright, but they're so far away we can hardly see them, or they look dim to us. So the apparent magnitude is what they look like to us. Now the absolute magnitude is what they really are. Now that's a little bit of a complicated thing, how we get that, how scientists, I can't do that, how scientists decide their absolute magnitude. They use that with distance, and he said he'll explain that later to us. Now turn on over get the absolute and apparent magnitude straight. Okay, I didn't put anything on the board, but I probably should have. Turn over here to the page 407, and you have a Hertz and a Russell diagram. Those are two scientists in 1910 put their information together, and they compiled a graph or a diagram to put the stars on. So you have their absolute magnitude over here on the upright and then the side. And so now look, the brightest ones are up toward the top. Okay, the negative 10 is brighter than 15 at the bottom. Okay, that tells you how bright they are. And then the other way, you have the temperature. But now listen, the red ones aren't the hottest. The cold ones are the hottest. Okay, so now get this straight. This is very tricky, this diagram, but once you understand it, it makes sense. Okay, the blue are the hottest, and up at the top is the brightest. Okay, so if you was get the brightest star, the hottest star, you would be up there at the O and the negative 10. And if you look at your page on 2-7, you would be the top left side of that diagram as the hottest and brightest star. Now, it may not look like that from us on Earth, but it is that way. And you kind of see a main stream going down through there. Those are called main sequence stars, and they fall in this bracket. Look at our sun, he falls in there. So that gives you a little picture where our sun at. He is not the hottest, brightest star out there. Hottest, brightest star. What for term is that now? There are white dwarfs. Okay, we'll take a look at them. You see, they are not real bright. They're kind of down there, down below the mainstream. We have the red giants. You see, they're up there in that corner. And then we have the supergiants. They're up along the top. That's the different brackets of stars. They're the classification. 90% of the stars that scientists have studied are in that main sequence, that stream of stars. 90% are in there. Now turn the page over to page 408, and we'll talk about a few of them. I don't know that I'll be able to mention all. You should look at the red giants. The red giants get their names as huge stars. The red giants, the core of a red giant is significantly hotter than a sequence star. So a red giant is dangerous. Don't touch him. He's hot. They're high. If you look, they're high on that diagram. The red giants are over there. They're high. Even though they're not a blue star, they are a big, hot, huge star. Supergiants are the hottest, are the highest though. Look at the supergiants. They're just scattered out. There's not a lot of them, and they're kind of scattered out from B to K. But you could get some supergiants that are extremely hot. They're rare though. Supergiants are not a common star. And let me see. I was going to talk about our sun just a little bit here. On the end of on page 409, it talks about just a little bit about our sun, how he's just the right brightness, he's just the right temperature to sustain life on a planet. Most stars are either too bright or too hot or something, and they couldn't sustain life. So that brings you back to this one vital foundational point. There had to be a designer for these stars to make them all work properly. There had to be a designer. There is a creator. Okay, let's go. You can answer your questions there on 16.5, 16.6, 16.7. Are red, I won't go 16.7 is a fun one. Are red giants cooler or warmer than most white dwarfs? I'll let you figure that one out. Look at your chart and it will help you. Let's talk about now, we're going to talk about variable stars. And variable means just exactly what it sounds like. They're not constant. They are basically two kinds of stars. There are pulsating variables and there are novas. And a nova is kind of like, it means new. Well, you say, oh, there was a new star born. Well, really, it's just a star that brightened up and then went dim. Bright, dim. Bright, dim. So I've got a switch. Turn it on, off. And they vary. Some do it yearly, some would do it almost daily, the way it says. It looks like a new star was being born. It's just simply brightening up that we can see it. And it makes a little explosion. A nova makes a little explosion that makes a bright light. When the star explodes, it emits a fraction of its mass, a shell of gas. This causes a temporary surge in its brightness, which causes the star to become more visible only for a short time. So a nova brightens up and then dies back down again. This book right here, I picked this book up at the Teachers Institute training last fall, and I put it back here on the bookcase, and I saw a few of you look at it, but most of you, it was kind of just a book. Well, really, I know this author, Morris Yoder, is from Georgia. He's talked in our church already. Yeah, you really, if you were here, you would really find this book interesting now that we're studying as scientists. So if you come by, you page through this book. I'm actually going to show you a few pictures. This book has got some very interesting facts about. It explains the nova. It explains the nebulum, the supernova and the nebulum. I should maybe at the bottom of 409. The extreme example of a nova is a supernova. A supernova is a true explosion of a star. Okay, a supernova that explodes. It just blows the pieces out of it. The star expands rapidly and brightly, enormously, and then fades away. A supernova is dead. It's sad, but he's gone. He blows up and he's just fragmented. He fades away permanently. He never comes back. You know, the pulsating variables, the variable stars, they brighten up, get dim, brighten up, get dim. They make a little explosion. They lose a little bit of their gases or whatever, but they're still there, and they explode again, but not a supernova. And that cloud that's left is called the nebulum. And so I'm going to show you some pictures here. These are clouds that are left of stars, and they've got them numbered. And he has got tons of pictures. That's an explosion again. It's got their numbers. Here you got another explosion, and here's this one star specifically. You see how it gets different sizes. It's different times as it's dying down. Yeah, it's got the dates on here. It's May 2002, and then this here is September of 2002, and this here is October, and then this in here is in December of 2002. They're all in 2002. Let's keep going here. I should show you a couple other pictures. There is one beautiful one. There's some of them. It's kind of hard to see those. They're just big old gases, explosion. Here is a significant one. You see there, and right down here by my finger, see that column sticking up? This is a supernova that's exploded, and so he's from a star. He's put off an enormous amount of light. It's been a huge one. You see that little column there? Now I'm going to show you that little column. He's got another picture of it back here. And that little column is right here. That's that little column that you saw on the other page. You see that column there? That's that little point in this supernova explosion. Now I'll turn back here and see if you can see him again clearer. Okay, see that little point right there? That little point is magnified here. And there you can see the point clearer. And these are supernovas that have exploded and they're done. They no longer will be coming back. They're dying. You have a picture on page 410. You have a picture of a supernova, and he is called the Crab Nebula, is his name. Or is he a pulsating star? Wait a minute, I might have. A pulsating star is getting bright and dim, and they are the ones that will actually last the longest. The pulsating stars keep making light bright and dim, and they hang in there longer than other nebulas. A very well-studied class of pulsating stars is the Cepheid variation class on the bottom of 410. It says these pulsating stars usually between 5 and 20 times the mass of the sun. They're 5 to 10 times as big as the sun, that explode. They make a bright flash and then they go dim, a bright flash and dim. And they can do it as quick as little as a day, from be bright for a day and then go dark, or they might be bright up to a year. They make a flash that will last for a year and then it'll go dark again. And then they will again do it later on. One more thing on 411, there are binary stars, and I talked about this yesterday about how our sun was just simply one star. There are a lot of stars out there that are binary. You know what binary? It's bi. Okay, bicycle has how many wheels? 2. So binary stars are 2 stars that are rotating in each other. And so part of the time you can see this star, part of the time you can be behind and you can see the other one. And so as they rotate, it's like this here, and you see one, you see the other one. They are, most of the time, they will not sustain any life. So yes, hope you enjoy this lesson. Don't forget about that yearbook article that you have to write unless you call me or text me, and maybe you can get a good enough reason not to. And, you know, unless, I wouldn't want you, if you were sick with the coronavirus, I wouldn't want you to have to write a yearbook article. Yeah, just do your schoolwork. Catch you later.